Welcome everyone to today's ANC seminar talk. Today we're lucky to have Vikrant Singhal, who will be talking about differentially private statistical estimation. Vikrant is a PhD student at Northeastern University, and he's done a lot of really cool work in his PhD about differentially private statistical estimation. In particular, I think some of the stuff he's talking about today will cover work that he did while visiting Waterloo last fall. He visited me last fall, and we had a really great time, did some, I think, really cool work. So without further ado, Vikrant, take it away.
All right, thank you, Gautam. Let me share my screen. Cool, it's visible, right?
That looks good.
Okay, cool. All right, so hello again. I will be talking about differentially private statistical estimation. This is based on
Did we lose him?
Yeah, I was wondering if it was.
I did.
Yeah, I did too.
I did too.
I'm sure he'll be back in a sec. All right, we got him back. Cool.
Yep. Let me get back to the PowerPoint again.
Sounds good.
Okay. Okay, so let me start by introducing statistical estimation first. We have an unknown distribution P from which we can sample as many points as we like. Our goal is to accurately output an estimate Q of P. Here, the aim is to estimate the required parameters of P with high probability, whilst using as few samples as possible, ideally with low runtime. This is a pretty standard setup that is generally used in stats or ML books for this topic. Okay. Yeah. However, there's a catch. Releasing raw statistics, even as simple as the empirical mean, can reveal information about the participants in the dataset, as was shown by Dinur-Nusin in 2003, and in the survey by Dwork, Schmidt, Steinke, and Ullman. This becomes worse when the dataset has potential outliers. So let me illustrate this via a simple example. Suppose we are picking people from a population where the salaries follow a well-behaved Gaussian distribution, and we want to calculate their average salaries. In the first data set, the average salary is 10,000, which is pretty easy to see. So let's look at the second data set. It's just the first data set with an additional row. That third person has salary 1 million and is a complete outlier. Now, the average salary in this data set is much more than 10,000. So if you know that there is that one person in the population whose salary is huge, then just by looking at the average, you can tell whether that rich person is in the data set or not. This is something we want to avoid. So we want to protect the privacy of everyone, regardless of whether they are outliers or not, which means that we want privacy guarantees even in the worst case. Therefore, this is the picture we want. It's the same as the last picture, but with one difference. That is, we want to output the statistics in a private way, even in the presence of that red outlier. The additional goal of privacy entails that the algorithm M should not reveal too much about any single sample in the worst case, and this should hold for all samples always, regardless of the distribution they're coming from. A little more formally, we want our algorithm to be differentially private. This means that for any pair of datasets that differ on at most one sample, the output distributions of our algorithm on the two datasets, mx and mx prime, must be closed. By closeness of mx and mx prime, I mean in a particular metric. And there are multiple ways of defining this closeness, such as concentrated DP, truncated CDP, and Renyi DP, and more. But the one that I'll be using throughout this presentation is the well-known epsilon delta DP, or approximate DP. Now, you don't have to remember this formal definition for the purpose of this talk. All you have to know is that it is quantified by parameters epsilon and delta, and the lower these parameters are, the higher the privacy we get. So typically, to achieve privacy, we add random noise to the value of a function that is large enough to mask the effect of changing one single sample in the worst case. That is, we obscure the samples by adding random noise. Formally, we define the sensitivity of a function f to be the maximum change in the value of f by changing one single sample. As an example, in this picture, we are summing 5 numbers between 0 and 10. By changing one point, that is, say, x1, we can change the sum by at most 10. So the sensitivity is 10. Then we can output the sum of fx and some Laplace noise, whose standard deviation is calibrated to the sensitivity and the privacy parameter. And this is commonly known as the Laplace mechanism and is epsilon-differentially private. And we'll be using this for mean estimation of one-dimensional distributions. And this is it for the basics of differential privacy. Any questions about the building blocks? I'm going to be giving awkward pauses like these throughout the presentation, so feel free to interrupt. Okay, I'll move on. So let's talk a little bit more about private statistical estimation. As I said, privacy has to be worst case requirement, and this makes simple statistical tasks such as mean estimation very hard. The accuracy proofs of these algorithms usually go about by assuming data from a particular source. But for the purpose of privacy, the data could lie anywhere and could be from any source. So we must account for every possible situation for privacy assurance. The literature shows that privacy is not achievable without additional overhead in sample complexity. And since it's typically achieved by adding random noise, we need more samples to cancel out the effect of the noise. And my goal has been to minimize this additional cost in sample complexity. So let's talk about some of the challenges in private statistical estimation to get some more context. Simple tasks such as mean estimation on real data could have infinite sensitivity because we could move a point in a data set arbitrarily far from the original position. So it is kind of important to know some kind of finite range for the data. As an example, suppose we want to estimate the average height of people from a population. The height of a human could range from 0 centimeters to infinity. And as we can see, this is clearly bad for the purpose of adding noise for privacy because the sensitivity is infinity. So it is safe to assume that the height of a human ranges between 0 centimeters and 500 centimeters. Although we are yet to see a human who is like 5 meters tall, but let's go with it for now. So let's do a little follow-up on the previous slide. Even if you have some prior knowledge about the data, there could still be some issues. The range of the data could be huge and unrealistic, as we saw, which could blow up the sample complexity, or which would blow up the sensitivity, resulting in huge amounts of noise being added for privacy, which would blow up the sample complexity. So we want to get a more realistic and tighter range of the data. Now, in the picture, the range of the data is initially 5 meters, which is pretty big and unrealistic. So while doing private estimation, if we add noise to empirical estimates calibrated to 5 meters, we will end up adding too much noise, and we'll thus need too many samples to cancel it out to be accurate. But suppose almost all of the heights lie between 140 centimeters and 200 centimeters. So the range is 60 centimeters, which is a tenfold decrease from the previous range. If you can somehow locate that data, that is, estimate the true range of the heights, we can reduce the range down to 60 centimeters and significantly reduce the noise we add for privacy. The way to do this kind of range estimation is always not so obvious and be quite tricky at times, but we'll see how to do it. So the next issue is that the width of the data could be varying depending on where it comes from. For example, when the data comes from a Gaussian, it decays quickly, so the range of the data becomes small. On the other hand, if the data is coming from a heavy tail distribution or heavier tail distribution, it could lie over a much wider range despite having the same mean. The challenge here would be to find the right length to limit the data within. Another challenge could be that the data could reside within sets having weird geometries. That is, the shape of the data could be pretty skewed. For example, the data could be coming from some unknown high dimensional Gaussian where some of the directions of the Gaussian are super long while the others are super short. Again, we have no prior knowledge about the range of the data, so it is a pretty big task by itself to see where the data lies. And finally, the data could be in the form of clusters that are overlapping or are far apart, like when it comes from mixtures of Gaussians. So there's no guarantee that the data would lie within a nice, well-defined shape. In these cases, getting to know where the data lies itself could be very tricky. So yeah, that's what we are going to be focusing on. And these are some of the challenges that I will be addressing in this talk. Any questions so far about anything I've said yet? Okay, I'll move on. With this motivation, I will introduce an approach called locate and estimate. This approach calls for finding the narrowest meaningful range for the data, truncating the data to within that range in a way that we don't lose too much information about the distribution, and estimating our statistic using the truncated data. This would help with our goal of having low sample complexity because the sensitivity would be reduced. So fewer samples would be needed to cancel out the noise we add for privacy. Therefore, the goal is to find the narrowest range possible for the data. Now, depending on the picture I showed you, we could be using different variants of this locate and estimate approach based on the complexity of the data range. It could be a one-shot location method, or it could be a complex iterative method. I will be illustrating both in this talk, but will focus mainly on the former by showing its application in mean estimation. Note that this idea of coming up with such low sensitivity estimators is not uncommon. We use this approach in new settings to get optimal results. Cool, so let's start with the simplest variant of the locate and estimate first. This is the one-shot location method, and I will illustrate this via the problem of mean estimation. Mean estimation is a fundamental problem in statistics that says, given IID samples from a distribution with mean mu, can we estimate mu? Without privacy, it has been studied extensively in the past in different settings and metrics, for example, under bounded moment assumptions and sub-Gaussians. With privacy, however, there hasn't been as much work yet. Recently, Karba and Vadan gave algorithms for mean estimation of one-dimensional Gaussians. Barber and Ducci studied the problem of mean estimation of heavy tail distributions under a stronger definition of heavy tail distributions than ours. So that means that if a distribution is heavy tailed under their assumption, it is going to be heavy tailed under our assumption. And we give strong upper bounds and lower bounds for mean estimation of heavy tail distributions or heavy tail data and high dimensional sub-Gaussians. So let's talk about heavy tail distributions. By heavy tail distributions in d dimensions, we mean that their kth moment is bounded in this case by 1. And the goal of the estimator is to estimate the mean to within L2 distance alpha. Now, without privacy, the sample complexity for this is d over alpha squared. It's the same whether we are looking at very heavy tail data, that is just with bounded second moment, or if you're dealing with the other extreme, that is sub-Gaussians. With privacy, however, things change. We get a hierarchy of sample complexities based on k. For example, the overhead due to privacy for bounded second moment is d over epsilon alpha squared, where epsilon is the privacy parameter. And for sub-Gaussians, it is d over epsilon alpha, which was shown by us 2 years ago. So I'll formalize these things now. Our first result is about mean estimation of heavy tail distributions in one dimension. Given sample access to the one-dimensional distribution with mean mu and kth moment bounded by 1, we want to privately estimate mu. So we give an epsilon delta dp algorithm for the same. The non-private sample complexity for this is 1 over alpha squared. The overhead due to privacy is 1 over epsilon times alpha to the k over k minus 1. Notice that we establish a hierarchy of sample complexities based on k, which is provably optimal. Yeah, it's optimal. And for the rest of the presentation, I will assume that the mean lies in the interval -1 and +1, because we can locate such a range using prior techniques. So the main challenge would be finding the right width of the data to truncate it within. Okay, so let's see how we do it. I'll start with the warm-up private algorithm first. We have points x1 through xn from the distribution. We truncate these points to within minus O of n to the 1 over k and plus O of n to the 1 over k to get points y1 through yn respectively. Using Chebyshev's inequality and the union bound, the points must lie within, or more like all points must lie within this interval with high probability. Now, the sensitivity of this empirical truncated mean is capital delta, the length of this interval over n. So we just output the sum of the empirical mean of these truncated points and some random Laplace noise calibrated to delta. This is differentially private, but the important thing here is that the sample complexity is 1 over epsilon alpha, the whole thing, to the k over k minus 1, which is suboptimal. This is because even though the bias of this estimator is low, the noise due to privacy is large because the sensitivity is very high, since this interval is too long. So we have to shorten this interval somehow. And this is our optimal algorithm. This time we do even a tighter range estimation, but in a way that a tiny fraction of the points may lie outside this range. Let R be equal to the max of O of epsilon n, the whole thing to the 1 over k, and O of 1 over alpha to the 1 over k minus 1. We truncate all the points to within minus R and plus R and output the noisy empirical mean, same as the previous algorithm, but with just a tighter range. Now, with this algorithm, we have a sample complexity of 1 over epsilon times alpha to the k over k minus 1, which is optimal. This is because in this case, the bias is slightly higher, but the noise added is much lower. We'll actually show that the bias and the noise are now balanced. Okay, so here's what I mean by that. When this interval is too large, we hardly lose any mass from the distribution. So the bias is very small, but we end up adding too much noise for privacy because the range of the data is big. But when the interval is too tiny and is very skewed, we lose a lot of the mass and the bias is huge, even though the noise due to privacy is much smaller. So we want to find some middle ground, that is, truncate enough that the range of the data is small, thereby decreasing the noise due to privacy, but at the same time, not truncate so aggressively that the bias blows up. With that idea, I'll go to the proof of the main theorem. We first formally define what truncation actually means here, even though we have used this implicitly a few times before. We use a pretty standard definition. let x be the random variable from the distribution and y be the random variable such that if x falls within -r and +r, y equals x. Otherwise, it equals the boundary point x is closest to. The first result about this random variable y is that it has low bias. It means that the expected value of this random variable is very close to mu. The second result is a standard fact about sampling error that says that the empirical mean of the points from any distribution with bounded kth moment is very close to the true mean. The proof of this second lemma is super chill, so I'm just going to show you the proof of the first lemma about the bias being low. By linearity of expectations, the LHS gets split into two parts when x is less than -r and when x is more than +r. There's also a third term that I didn't write, where x lies in the interval -r and +r, but that term is 0 because y equals x in that interval. The next line follows from triangle inequality. Now, we have to bound these two terms. And the nice thing is that the proofs for the bounds on the two terms are symmetric. So we will just end up bounding the first term and the second term would follow. So the first line of this holds because we add and subtract mu in the parentheses and apply the triangle inequality. The next line holds due to Euler's inequality. And the next line holds because of our bound on the kth moment and applying the generalized Chebyshev's inequality for the probability terms. And the final line holds because of math, alpha plus alpha equals 2 alpha. So yay. So yeah, it's a pretty simple and cute proof, but it's crucial for our algorithm to work. So with these two results in hand, we just need the error due to privacy to be small. And this is exactly what happens because the range of the data is very small. The error due to privacy is O of r over epsilon n with high probability. And for that to be less than alpha, it is enough to have n more than 1 over epsilon times alpha to the k over k minus 1. And the theorem follows from triangle inequality. So this is why our algorithm works, and that is it for the 1D upper bound. Any questions or comments about this so far? Nothing? Okay, cool. All right, so now I'll briefly talk about the lower bound for this 1D case. This will show that our results are optimal. Sorry, one sec, something bad is happening on my laptop. Okay, yeah, it's fixed, never mind. Okay. We reduce the problem of hypothesis selection to the problem of mean estimation. This would imply that learning to within distance alpha over 2 would enable us to distinguish between two distributions that are alpha apart. So this is our problem instance. Let P be a type of Bernoulli distribution with parameters P and tau, such that with probability 1 minus P, we get 0, and with probability P, we get tau. We define Q to be a constant distribution, that is, one that outputs 0 with probability 1. This implies that the mean of P is P tau, which we define to be alpha, and with P at least alpha to the K over K minus 1. And the mean of Q is 0, which means that the means of P and Q are alpha far apart. This also implies that the kth moment of P is upper bounded by 1. Now we just use the lower bound for hypothesis testing. The lower bound implies that distinguishing between P and Q would take at least 1 over epsilon times alpha to the K over K minus 1 samples under epsilon dp. And this implies a lower bound for mean estimation as well. It's the same as our upper bound, which shows that our upper bound is optimal. Oops. The intuition is that the two distributions are close to one another in TV distance, in total variation distance. So the data sets that are generated by them are going to be very close too. So differential privacy entails that the output distributions on those two closed data sets are going to be very close to each other as well. Therefore, to have significantly different output distributions, we want the data sets to be sufficiently far from each other by having more samples to be able to distinguish between their outputs. And yeah, that's all I'm going to say about the lower bound. Any questions, comments? Okay. So I'll briefly talk about our second result, which is about mean estimation of heavy tail distributions in high dimensions under approximate DP. Without privacy, we can do that using d over alpha squared samples, as I mentioned before, by simply computing the empirical mean. For the purpose of private estimation, we give an epsilon delta dp algorithm that takes d over epsilon times alpha to the k over k minus 1 additional samples to be accurate. As before, the non-private sample complexity is independent of k, and we get a hierarchy of sample complexities that's based on k. So the algorithm for this is just the same as that of the 1D case, that is, truncate aggressively and learn. And the analysis is also pretty similar.
I think we might have lost him again. Hopefully get him back in a minute.
Why does this keep happening to me?
Yeah, weird. I don't know.
Yeah, the second time. Okay, let me share my screen again. Okay, I'll start.
Yeah, start from the start of this slide.
Oh yeah, from the start of the slide or the beginning of the presentation?
Preferably just the start of the slide.
Okay, cool. All right, so let me start with this again. Yeah, okay, so this algorithm for the 1D case is pretty similar or exactly the same as that of the 1D algorithm, truncate aggressively and learn. And the analysis is also pretty similar similar to that of the 1D case. We will find a rough estimate of the mean coordinate-wise using the 1D algorithm, and we call that estimate P. And then we truncate all the points to within a ball of radius square root d over alpha to the 1 over k minus 1 around P. And this is the location step. And we finally output the noisy empirical mean of the truncated points. So that's the algorithm. And the challenge is to balance the bias and the noise due to truncation. And it's just, the proof of that is also pretty similar to that of the 1D case. So therefore, that's all I'm going to say about this. Any questions, comments? Okay. Now I'm going to talk about our third result, which is about mean estimation of heavy tail distributions in high dimensions under pure DP. This is a bit different from the locate and estimate strategy though. Without privacy, we can estimate the mean using d over alpha squared samples, as I mentioned before. And for the purpose of private estimation, we give an epsilon-dp algorithm this time that takes d over epsilon times alpha to the k over k minus 1 additional samples to be accurate. For pure dp, we need some bound on the range of the mean, which in this case is r, that bounds the coordinates of the mean. In the sample complexity, this parameter r could be very large without hurting the sample complexity. And finally, this sample complexity is optimal. And this was shown by Barber and Ducci for this problem much before our work. So let me give an overview of the techniques involved. The algorithm is based on Sheff estimators, which is a tournament-based approach used for density estimation and more. This framework was first made private by Bun, Kametz, Chanka, and Wu for the problem of hypothesis selection. They do it using the exponential mechanism, and so do we. For those who don't know what the exponential mechanism is, it assigns a score to the candidate output points based on the given data set, and with high probability, outputs a point with high score. And that algorithm is epsilon-differentially private. Here, the score function is based on a series of games among all candidate output points. But this is kind of where the similarities between the BKSW19 paper and us end. While they do comparisons among distributions, we do comparisons between points in the output space that could be candidate means for the distribution in question. Also, our comparisons are done after reducing the problem from d dimensions to 1 dimension. I'll talk about this more in the next slide. Okay, so we first define a comparison or a game between two candidate points P and Q. We will use this definition to define the score of points in the output space. Let X be the data set. Project X onto the line P minus Q and truncate close to P to get data set Y. Let mu prime be the empirical mean of Y. An outcome of a game between P and Q is defined to be a tie if P and Q are close, a win for P if mu prime is closer to P than it is to Q, a loss for P otherwise. And this is the whole reduction to the one-dimensional problem as I mentioned in the previous slide. Now, the score of P is defined to be the minimum number of points of X that have to be changed for P to lose at least one game. We show that points like P that are close to the true mean, mu, have high score with high probability. This is because they're winning by default against points that are far from mu. The points like Q and R that are far from mu have score 0 with high probability. This is because they lose by default against points that are close to mu. The intuition for this is that when truncating around a point that's close to the mean, the bias is low, so the points would tend to concentrate around it. So we will have to move too many points to move the empirical mean far from P. So, and finally, we show that the sensitivity of this score function is 1. It's a technicality. And then we invoke the exponential mechanism. And this gives us an accurate estimate of mu. And that's it about the pure DP case and mean estimation in general. Any questions or comments? I know this was like a pretty complicated construction. It's a pretty weird cover-based construction, but yeah, any questions, comments?
If I remember correctly, you're assuming that the mean is in some bounded range, is that correct?
Yeah.
So for this score function,
yeah.
Do you also have to assume that the data are bounded?
Sorry, for the score function, do I have to assume what?
That the data are bounded as well as the mean, or can the data be unbounded?
So the data could be essentially unbounded, but because we are truncating after projecting onto the line P minus Q, we truncate close to P. So like even if the data is like unbounded, it will just get clamped to within this interval. We just assume that the mean is bounded so that we can get some rough idea of what candidate output points we need to choose from.
Thanks.
Yep. Any other questions? Okay, so far you've seen the locate and estimate paradigm as the one-shot process. There are other complex variants of it too. I'll talk about these other applications in the form of two statistical estimation problems: covariance estimation of high-dimensional Gaussians and parameter estimation of mixtures of high-dimensional Gaussians. There's also a third application, which is mean estimation of product distributions over binary strings, but I'll not talk about that here because its algorithmic ideas are pretty similar to that of the covariance estimation algorithm. So yeah, and also no need to worry, I'm not going to be boring you with low-level details again. So everything's going to be super high level. So let me start with an iterative variant that would be used for covariance estimation of high-dimensional Gaussians. We have a different problem here. We got to estimate sigma, the covariance, in total variation distance. So the directions of the covariance have to be estimated, or the short directions of the covariance have to be estimated more accurately than the long ones for this metric. So one-shot location and estimate locate and estimate method will not work in this case because we have to make sure that the noise we add in short directions is much smaller than the noise we add in the long directions. And we cannot do this without knowing the shape and the alignment of the covariance beforehand if we are to do this in one shot. And by the one-shot naive estimator, I mean that we simply output the noisy empirical covariance. And this algorithm is suboptimal because the sample complexity depends linearly on the eigenvalues of sigma, which is something we really want to avoid. So we resort to an iterative variant, which we call private recursive preconditioning. The goal of this is not just locating the data, but also shrinking the range of the data. That is, it shrinks down the directions of the Gaussian so that it becomes sphere-like. Then using the naive estimator, we can estimate the sphere-like Gaussian and then expand our estimate to the original form using the inverse of our transformation. So the question here is, how do we obtain such a transformation? This is how we do it. In this picture, the blue ellipsoid is the true covariance with eigenvalues bounded by kappa. In the first iteration, we apply the naive estimator to get the pink estimate of the covariance. It's a bad estimate of the blue covariance, but not super bad. The long directions maintain their lengths because they can tolerate more noise, but the short directions get affected more. Note that this noise is large, but not too large, as I said. That is, the directions that appear long are not long just because of the noise, they are themselves long. And the other directions which appear short are actually short as well, and not just because of the noise. So we can identify the longer directions accurately and shrink them by a constant factor without hurting the shorter ones. In the next round, we can repeat the same with lower noise since the sensitivity is lower because the covariance has shorter directions than before. And this is how the iterative variant of the location strategy works. And that's it for learning Gaussian covariances. Any questions or comments? We are almost done. Okay, so let's talk about the final variant that I've dealt with. When the data is in the form of clusters coming from mixtures of Gaussians. The goal is to estimate each component of the mixture accurately. This time, the problem with the one-shot private learning is different. Here, the Gaussian components could be of different shapes and sizes. They could be potentially overlapping or be far apart. There is no well-defined shape that tightly bounds the clusters. Also, we don't know what sample comes from which Gaussian. So to learn the individual components, the goal is to identify the clusters corresponding to each component, which would help us to locate the data within an estimate. Hence, we'll be using private clustering to locate the individual components. Once we identify the clusters, we can learn the individual components using the Gaussian learner mentioned in the previous slides. In this process, we will be using tools like private PCA for dimensionality reduction, followed by private ball finding algorithms. So now let's look at this picture for a second. In this, there are clusters close to each other, forming superclusters, and the superclusters are far from one another. The goal is to locate these superclusters in step 1, which would help reduce the sensitivity for private PCA that would be used in step 2. And then private PCA would help in segregating the largest component in the supercluster from the rest, which we would then locate in step 3 using a ball finding algorithm. We can then learn the isolated component using the Gaussian learner from the previous slide. And we do this till we have located and estimated all individual components. And this is it about learning mixtures of Gaussians. Questions or comments?
Sorry, could you describe exactly what the difference between the superclusters and the balls are?
So yeah, I mean, these things, the cluster which are like super close to one another, can you see my cursor?
Yeah, I can.
Yeah, so like these things, so this is one supercluster, this is one supercluster, and this is one supercluster. And because these are pretty close to one another and these groups are far from each other. And we capture these superclusters in balls to like sort of isolate them so that they can be treated as independent subproblems, essentially. Does that make sense?
Yeah, that makes sense. Thank you.
Yep, sure. Any other questions?
Sorry, just as a follow-up, do you require
Yeah.
some separation between the superclusters? Like how much separation do you require before you like consider two superclusters to be distinct?
So we don't require separation between superclusters. We essentially, that's something our algorithm is going to find by its own. If the gap between superclusters is like large enough means like if the dimension is d, if it is of the order square root d or more, it should be able to identify the superclusters by itself. But the separation that we assume is between the individual components. We assume that each individual component is like at least certain distance apart.
Got it. Okay, thank you.
Yeah. I'll wait for more questions. Okay, cool. So that's it. I'll end by summarizing what I talked about. Locate and estimate is a pretty simple and common theme behind private estimation. It's a pretty versatile approach for private statistical estimation problems. I demonstrated a few applications of that approach. They include mean estimation, for which we get optimal results, covariance estimation of high-dimensional Gaussians, and finally, I gave a little overview about learning mixtures of high-dimensional Gaussians. So that's it. Thank you for listening.
Cool. Thanks a lot, Vikrant, for your talk. Yeah, are there any? Oh yeah, typical Zoom clapping. Okay, are there any questions from anyone? I'll ask, what do you think is next? Like, these are some good foundation fundamental results, but like, where do you go from here?
So there's one problem that I'm interested in, which is like learning like mixtures of Gaussians, but with just the separations currently we have right now are not super great, as you probably know as well. You're the co-author. So yeah, the separation condition is dependent on the mixing weights, and that is something I want to remove. I just want it to be dependent on either the dimension or just the number of the components, which is usually a standard case in the non-private literature. So that's something I want to deal with. And there are other problems which are like slightly different, but have similar flavors, like hypothesis testing or different kinds of hypothesis testing for different kinds of data that I'm interested in. So yeah, these problems.
Your sound got really crunchy towards the end there, but it was fine. Yeah, I don't know. That's a good question. I mean, recently there's been a lot of work in learning mixtures of Gaussians. without
Yeah.
separation condition, including in like the latest stock, for example.
Mhm.
The techniques are significantly more technical, so it would be interesting to see whether those could be privatized appropriately without having to pay more.
Mhm. Yeah.
Okay, any other questions? Cool. If there's no other questions, I'll stop recording, but then we can hang out a little bit longer while and ask any questions or two. Scared task right now.